Kinetics of batch fermentation. In this figure, uh, this is the exponential phase, and this is the stationary phase, and this is the decline phase. This is the initial lag phase. During the lag phase, there is no change in biomass. Only the change in biomass can be seen in exponential phase and in decline phase. So the kinetics can be calculated for the exponential phase and for the decline phase. Remember, for the exponential phase, specific growth rate minus specific death rate is greater than 0, and for the decline phase, specific growth rate tends to 0. So rate rate which can be written as dx divided by dt is directly proportional to x, where x is the biomass concentration. Now removing the proportionality, we can write dx by dt is equivalent to mu x, while mu is the specific growth rate. Now rearranging this equation and integrating this integration, we'll write it as x naught integrated from x naught to x initial population to final population dx divided by dt is equivalent to 0 time to t time mu dt. So solving this, we'll get ln x divided by x naught, which is equivalent to mu dot t. Taking antilog, we will get x divided by x naught is equivalent to e raised power mu dot t, or we can write x is equivalent to x naught e raised power mu dot t. So in this equation, we can say this x, the initial population, increases exponentially. This x initial population increases exponentially. Now if we have to calculate the doubling time, doubling time is a time in which the number of initial population doubles. That is, the x will become 2 times x naught, 2 times initial population. We know ln x divided by x naught is equivalent to mu t. Now put this value in this equation, we will get ln 2x naught divided by x naught is equivalent to mu t. This and this will get cancelled, and we will get ln 2 is equivalent to mu t, or we can say t is equivalent to ln 2 divided by mu, which is equivalent to 0.693. divided by mu. So the doubling time is equivalent to 0.693 divided by mu. We can represent this through the graph. There is an exponential increase from initial concentration to the final concentration. X is equivalent to x naught e raised power mu t, or we can express it in logarithmic graph, and we will get straight line slope equivalent to mu specific growth rate from initial concentration x naught to x. So similarly for the death phase, for this phase we can calculate the kinetics like for the exponential phase, and the final equation will be x is equivalent to x naught initial population e raised power minus kt dot t. This uh, negative sign represents the decrease in biomass due to the depletion of the nutrients. Hope you understood this. Thanks for watching.